This is my unit design by Ryan Ellison. It's over impulse and momentum, and it's designed for AP Physics 1. For this project, I will be incorporating Gagne's 9 steps of instruction. Step 1 of Gagne's steps of instruction is to gain the student's attention. Basically, I do this at the start of a unit by showing the students a phenomenon in which I ask for their observations, and then I ask, what can we measure about their observations? It's a form of guided inquiry where students pretty much design the lab with a little prodding from me. The second step is to provide clear learning objectives, and we are mandated, the teachers in my district, to put up our targets, also known as learning objectives, on the whiteboards in the classroom so that students understand what is expected of them at all times. Step 3 is to stimulate the recall of prior knowledge, and I believe that physics lends itself to this pretty nicely in that students kind of understand how the universe works around them. At least they might have some preconceptions, but overall they do understand how the world works. They just don't really have the mathematics behind it to make predictions. The fourth step is to present the material. Now this is where I really put this in the hands of the students as they are the teachers. I'm more of a guide on the side rather than a sage on a stage. And with that, I use the modeling method of instruction, and I allow the students to present their lab results to the class, and they derive all of the equations that we utilize throughout the entire year from experiments. So I don't give them any equations blindly. The fifth step is to provide guidance for learning, and I kind of touched on that in step 4. I do that using the modeling method of instruction as well as Socratic dialogue, in which I ask students a lot of questions, which leads to the sixth step, which is eliciting performance from the students. And I do that by asking guided questions, Socratic dialogue. It's really the students are forming their own procedures and ways of thinking about the universe. Step 7 is to provide students feedback. I do that using exit slips along with half-sheet quizzes. We also have formative and summative assessments along with problem-based learning activity and a end-of-unit lab practicum. Step 8 would be the assessment portion of their performance, and I do provide feedback on their assessments, typically within a day. And to assess their performance, they do get formative assessments, such as those exit slips along with the half-sheet quizzes. And the final step is to enhance the retention and transfer of the learning. And I do this with the problem-based learning at the end of the unit, along with the end of the unit lab practicum, which we'll explain in a little more detail. The technology used will be Acer computers. We'll use that to collect data from our labs. We'll also use Excel, where students can place their data into Excel and create equations so that they don't have to go through the menial tasks of computation of lots of equations and data. Students also have the option to use Google Sheets. If they don't finish their analysis of the data during class, they can collaborate online using Google Sheets. We'll use Verniers Graphical Analysis, which is a graphing program, along with Verniers Logger Pro, which is a data acquisition program. What you see on the right of the screen in those pictures is a Lab Pro, which is the interface that connects the force sensor along with the motion detector and sets it up to the computer so that Logger Pro can graphically display data. I will also incorporate the University of Colorado online simulations. The technology adds a ton of value to this unit, mainly because students can use the graphing software along with the data acquisition software, so Vernier, to efficiently find the slope of a line with one click of a button, rather than finding the rise and the run of a best fit line that they create on paper. The program also has the ability to calculate derivatives and integrals from the graphs, which are created from the data acquisition software. If students didn't have a deep knowledge of calculus, it would take them upwards of 1 to 2 hours to do that. Now that we're using the computer software, it takes less than 2 or 3 minutes. All right, I'm going to give you a quick rundown of the day-to-day activities. Day 1 includes an impulse and momentum lab, and it's a 2-part lab. Part 1 is I show them a collision between a go-kart, a Pasco go-kart, into a wall, and the force sensor is hooked up to the car. So you can measure the force of the collision, and it just depends on what you're banging into. So I ask the students what factors affect the force in a collision. Students will work in groups of no more than 3. I do use flexible grouping based off of the interest type of the collision and material. And then the students will whiteboard the results, and they will present their findings to the class in order to describe the model that we'll use for the rest of the unit. Here's a sample graph. Sorry about the fuzziness of the screenshot, but basically what we have here is, this is an example of Logger Pro's graphs from the data acquisition software. So on top you have a force versus time graph, and you notice that there's a spike even though it's kind of a soft curve. But this is an example of the car crashing into foam. The students also have the option of crashing into the wall, into a balloon which replicates an airbag, any other material that they find. And the whole point of the lab is to determine what factors affect the force. And as you can see, if you banged into a wall, it'd be a sharp triangle rather than this soft curve. So hopefully the students grasp the concept that if you increase the amount of time you're in a collision, the force decreases. That's because force is inversely related to time. The second graph is a position time graph, and that's from the motion detector. It demonstrates the motion of the cart as it goes down a ramp, an inclined ramp, and bangs into the wall and comes back. And the final graph is a velocity time graph, and that's useful for determining the change in velocity of the object. This is an example of a student whiteboard from the lab. I typically make sure that they have important and pertinent information, such as the graphs and explanations of what the actual graphs are and what's important about the graphs. And then to the right, you can see the equations where they are actually deriving an equation and filling in sample calculation for the impulse of the collision. Impulse is denoted with the capital letter J. Now this group forgot units, which is pretty important, but that sometimes happens. Day 3, we describe the model that we've developed. Basically, momentum is equal to impulse, and the equation is F delta T equals M delta V. And I'll have students analyze the force time graphs that were created in the part 1 of the lab. And really, we're taking the integral, so we're using graphical analysis to one click take the integral of the force time graphs, which represents the impulse. And then I pass out worksheet 1 from the momentum unit, and this is really just where they get to practice applying the model. Day 4, we will whiteboard the assignment. Basically, I walk around and ask each lab group to put one problem on a whiteboard, and really I want their problem solving so that they can explain their process to the class and their procedure. I don't show them any procedures, I want them to create their own. So this is where Socratic dialogue and the modeling method really kick in. So after their presentation, the audience, which are the rest of the classmates, critique the whiteboard presentation. During day 5 and 6, I'll introduce part 2 of the Impulse and Momentum Lab, and really we're looking at what factors affect the momentum of an object during an inelastic versus an elastic collision. So we're comparing the two different types of collisions. Students, again, design and set up their own lab, and then they carry out their investigation. So it is guided inquiry once again, and we use all of the same instrumentations that we used in part 1. Day 7, we'll go over the lab results and talk about them. We'll discuss the importance of airbags, seatbelts, and crumple zones in automobiles with regards to collisions. And this is really pertinent and actually applies to these students because AP Physics 1 students are typically juniors and seniors who are 16, 17 years old who are driving automobiles. Day 8, we'll work on homework set number 16. It's just a set number of problems out of the textbook, and it's, again, practice using the models that we've developed now for elastic and inelastic collisions. And we'll typically go over them. I'll collect homework set 16, and I typically assign 2 or 3 problems that I actually grade for feedback. We will also assign for homework the collision lab simulation, which evaluates elastic versus inelastic collisions, and more specifically in 2 dimensions, which during the lab we only look at 1 dimension. The details of this can be found on my webpage that I designed for this project. It's a Weebly website, and the simulation is accessible at the University of Colorado simulation website. During days 9 and 10, I will introduce the lab practicum. This is where students look at an inelastic collision, and they need to determine experimentally the velocity of a projectile that's shot into a second object. So in an inelastic collision, the 2 objects stick together and move off as one. So for an example, one of the options, there's 6, is a dart gun. So the dart being shot into a box, and the box slides along the ground. So students can work backwards to figure out the coefficient of kinetic friction between the box and the table, along with finding the momentum of the box after the collision. Then they can figure out the velocity of the box right after the collision, and then they can work backwards using conservation of momentum in order to determine the velocity of their projectile. Students are also supposed to determine a second way to verify their velocity. So they're setting up 2 labs which they design. And they can use any technology available in order to do this. During day 11, the students present their findings to the class, and they can use any method of presenting. I have had a lot of students use a video. For some reason, high school students don't like to stand up in front of the class and talk. So it's a lot easier for them to just make a video and play it on the Apple TV. The audience then criticizes or critiques the group's experimental methodologies and asks thought-provoking questions to get at the heart of their lab. For the final project, it's a PBL, so a problem-based learning, and it's called A Day in the Life of John Henry, a Traffic Cop. Students are basically deployed with the task of figuring out who's at fault in a 2-dimensional collision. So like at an intersection, which car is at fault. So they have to use all the concepts of physics, conservation of energy, and then conservation of momentum, which we've been working on now for almost 2.5 weeks. They present their findings to the class, and they act like a judge and a jury to determine who's at fault, which is kind of what I talked about right there. Day 15, students are given a summative assessment, and I also send out a Google Form survey to their school emails addresses asking them for feedback on how the lesson went and how the unit went, especially deploying all of these new methodologies that I've learned from this class. Thanks, and I hope you've enjoyed my presentation.